Today we'll be talking about solutions. Here's a review. There are two types of mixtures: homogeneous mixtures and heterogeneous mixtures. Heterogeneous mixtures are mixtures that are not uniform in composition. They contain at least two or more ingredients or phases. In the context of mixtures, a phase is any part of a sample that has uniform composition. For example, when you mix oil and water, the oil and water don't mix completely. The oil and water are said to be different phases. Heterogeneous mixtures can be solid or liquid or gas. The components remain separate from each other, and they're often easy to identify. It's not difficult to separate these kinds of mixtures. Unlike with homogeneous mixtures, samples taken from different parts may have different composition. I can put my spoon in one side of the vegetable soup and scoop out a carrot, and on the other side I might scoop out a pea. Examples of heterogeneous mixtures: salt and pepper mixed together, ice in water, chocolate chip cookies, cereal and milk. Homogeneous mixtures, on the other hand, have compositions that are uniform throughout. A sample taken from one place in the mixture will look exactly like a sample taken from another place. Now, even though it's a mixture, the substance looks consistent and uniform macroscopically, and you can't pick out different components or use simple mechanical means to separate them. In a homogeneous mixture, dissolved particles which are too small to be seen are spread throughout the mixture, and the particles are too small to settle out. Now let's talk about solutions. Solutions are a special type of homogeneous mixture that's composed of two or more substances. The solvent is the component that's present in the greater amount. It's often water. It's a substance that other substances are dissolved in. The solute is the substance that's present in lesser amount. It's the substance that dissolves in and is dispersed throughout the solution. Gravity does not cause it to settle out over time. Solutes can be molecular or ionic compounds, and in ionic compounds, the ions typically separate. Solutes can also be metals in the case of alloys, which are a type of solution. We use the term aqueous to describe solutions that have water as the solvent. You will often hear the term aqueous solution, and you may see the symbol AQ in parentheses next to a particular chemical formula in a chemical equation, and this tells you that the substance has been dissolved in water. Aqueous solutions are one of the most common types of solutions used in chemistry. Many chemical reactions involve interactions between substances that have been dissolved in water. Solutions can occur in any state of matter. Although we usually think of solutions as being liquid, you can also have solutions of gases and solids. Air, for example, is a solution of gases. It consists of a homogeneous mixture of about 78% nitrogen, 21% oxygen, 1% argon, and trace other gases. Metal alloys are examples of solid solutions. Examples include brass, which is a solution of copper and zinc, bronze, which is a solution of copper and tin, and steel, a solution of iron and carbon. When you're dealing with solutions, especially in the liquid phase, we use molarity to refer to how concentrated a particular solution is. Molarity is defined as the moles of solute per liter of solution. It's very important to note that the denominator is liters of solution and not liters of solvent. In fact, when you make a solution, you're typically putting all the solute in first with a little bit of the solvent. You mix it up, and then you add additional solvent to this mixture until you have the exact volume you need. One thing to bear in mind is that solution volumes vary with temperatures. Solutions can expand and contract, so the molarity for a solution will vary at different temperatures. But most of the time when we're dealing with them, we'll be dealing with solutions at room temperature. Brackets are often used to indicate that you're referring to concentration or molarity of a solution. For example, if you see H2SO4 in brackets, you can infer that this is referring to the concentration or molarity of the sulfuric acid. Let's do an example of a molarity problem. Say we have 250 milliliters of solution that contains 35.5 grams of sodium sulfate. What is the molarity of our solution? Well, let's see what we're given. We have 250 milliliters of solution. That is 0.250 liters. Remember, since molarity is moles per liter, we will want it in liters. We have 35.5 grams of sodium sulfate, and our equation for molarity is moles of solute per liters of solution. Now, we need to find moles per liter. Here is our strategy. First, we're going to convert grams of sodium sulfate to moles. We'll do that by taking the number of grams we have and dividing by the molar mass. That gives us 0.2499 moles of sodium sulfate. Now we're going to take this and we're going to divide it by our volume, and we will get 0.9997 moles per liter. And we'll go ahead and round that up to 3 significant figures to get 1.00 molar. So we have a 1 molar solution. Let's talk about making dilutions. Sometimes the stock solution that comes from the chemical supplier is stronger than we need it to be. We need to dilute it so that it's usable and so it's safe. When you're making dilutions, you're decreasing the concentration and therefore the molarity of the solution. The number of total moles in your sample does not change, but you're increasing the volume of the solution, so the molarity does change. We can see this when we look at this particle diagram. We see on the left, we have a more concentrated solution, and you can see all of the solute particles represented in that diagram on the left. When you dilute it, there's a lower concentration. You see fewer solute molecules, and they are spread farther apart. We can derive a useful equation that'll help us with dilutions. We start with the initial concentration, the initial molarity. We'll call that M1, and that's going to equal N1 over V1, the number of moles over the initial volume. We can rearrange this to M1 V1 equals N1. Now, we're going to do this as well for the final molarity. So after our dilution, our final molarity will be M2, and that's going to equal N2 over V2. And we can rearrange that algebraically to M2 V2 equals N sub 2. Now, if we're just diluting a sample, we're going to keep the moles constant, so N1 equals N2. By simple substitution, we get the equation M1V1 equals M2V2. And we can algebraically rearrange this equation in many, many ways to solve for various different types of dilutions. Here's an example. We have 100 milliliters of a 2.0 molar solution of hydrochloric acid. We're asked to dilute the solution by adding enough water to make the solution volume 500 milliliters. What is the molarity of the diluted solution? Let's see what we're given. Our V1, our initial volume, is 100 milliliters. Our initial molarity, M1, is 2 molar, and that's the same as 2.0 moles per liter. And the final volume is going to be V2, and that's 500 milliliters. We need to find M2, the molarity after dilution. Our strategy is to use M1V1 equals M2V2. We're going to rearrange to solve for M2, and then we're going to plug our numbers in. M1V1 equals M2V2 becomes M2 equals M1V1 over V2. Now we plug in our numbers, and our final concentration is 0.40 molar, or 0.40 moles per liter. Writing it that way is okay too. Just an important note, often when you're doing molarity problems, you'll be given your volume in milliliters. If you're determining the molarity of a solution, you're going to need to convert milliliters to liters because molarity is moles per liter. However, When you're doing dilution problems, it's often okay to use milliliters. When you're doing dilutions in a lab setting, you're usually diluting to a certain number of milliliters and not liters. And with the M1V1 equals M2V2 equation, it works if you use milliliters, it works if you use liters, and that's fine. When you do dilution problems, also make sure your answers are in units that are the most practical for the lab you're doing. For example, 10 milliliters makes much more sense than 0.010 liters if you're using the typical graduated cylinder. So let's summarize. A solution is a type of homogeneous mixture. The solvent is the component present in the greater amount, often water, and the solute is the substance that's present in lesser amount, the one that is dissolved in the solvent. If a solution is aqueous, that means the solvent is water. Molarity refers to the concentration of a solution. It's reported as moles of solute per liter of solution. The equation M1V1 equals M2V2 is very convenient when you're trying to make dilutions of solutions.